up, we have one of our favorites. We have Marshall Cox, who is the CEO of Radiator Labs. Radiator Labs happens to be one of the superstar graduates of the MetaProp NYC 2015 Accelerator Program. Marshall is one of the smartest human beings I've ever met, an excellent CEO, and is running one of the fastest growing companies in real estate technology in New York City today, based in Brooklyn. Their technology is actually really interesting and really applicable to not just the owners of buildings who get a lot of value out of the technology, but also the occupiers of space, including residential tenants in buildings in New York City and beyond. So Marshall's here to tell you a little bit about the technology. We're very excited he's here to join one of New York City's own real estate technology startups, Marshall Cox, Radiator Labs.
My name is Marshall Cox. The company is called Radiator Labs. Our hokey tagline is bringing radiator heat into the 21st century. I've been told that we can have questions during this, so even during the presentation, if you have a question, if something's not clear, please raise your hand. I'm much more comfortable answering questions than presenting. A little background on myself. So I'm a huge nerd. I went to engineering all back undergrad and PhD. I was at Columbia University for my PhD back in 2008 and graduated in 2013. And during that time, I lived in a terrible, horrible steam-heated apartment. Who here has ever had to open their windows in the middle of the winter because they were too hot in their apartment? This is a question I always ask in New York City. It's a pretty popular question. So this is what I experienced. And my PhD is actually on something that has nothing to do with steam. I never thought I'd know this much about steam in my entire life. But I lived in this horrible place, and it was overheated, and I talked to my advisor. I spent a lot of time talking about this problem. And we came up with a solution that was certainly outside the realm of what people who work with steam systems typically think about. I'm a systems engineer, more or less. And so the idea that we came up with was this really simple cover to control temperatures. But before I get into how that works, I want to go into why this is a problem. Why are a lot of our buildings and our homes overheated in the middle of winter? And the problem isn't that steam, we're talking about steam here, steam heated systems, steam heated buildings. It's not that steam is bad. Steam is actually a great technology. Back when most of these buildings were built, pre-war buildings, there was no other technology to heat large spaces. There was no good water pumps and no good fans. So the only way to heat a large building was to boil water in the basement and let that steam rise up through pipes and heat rooms. And when these buildings were first built, they were actually magnificently balanced. It was amazing how well they did at balancing these buildings. They had rules of thumb that sized radiator, riser pipe sizing, radiator sizing. They understood, you needed bigger radiators on the north side of the building than the south side because of exposure to the sun. And they were just greatly built and obviously built to last. That's why they're still here. The reason why we have this problem is because we invented double pane insulating glass. And there are a few other reasons, but that's probably the primary. And when we changed, if you've ever lived in an apartment that's historically protected or has single pane glass for another reason, you understand that it leaks like a sieve. You can feel the cold just dramatically. And when we changed those windows, we dramatically changed how much energy those rooms needed to be heated. And if you have a room in a building that has one window and a room that has two windows, and you change those windows to more insulating windows, you completely change the amount of energy they need. But you have not changed the pipes or the radiators that supply heat. And so what happens is this room needs less energy, this room needs more. And you run the boiler until that coldest room in the building gets to minimum statutory temperatures. And now everybody that's in the building has been overheated. And we're talking about 80% of the building, just to meet the needs of that 20% by law. And so this is the issue that we have. This is why you've been opening your windows in the middle of the winter for the entire time you've ever lived in those steam-heated buildings. It's not just a comfort issue, obviously. It's an enormous environmental and financial disaster. About 10 to 15% of the housing stock, the residential housing stock in the United States is heated by steam. The Department of Energy of the United States and NYC estimate that we waste about 30% of the energy these buildings consume through overheating. So if you are burning 10 gallons of fuel to heat a building, you're basically taking 3 of those gallons, bringing it out into the street, and letting it on fire. That's how much waste we're talking about. And it sums to about $7 billion a year of wasted fuel. In New York City alone, that's $1.2 billion a year. I'll ask another question. It's the first time I've asked this question. How many people here have cleaned black crap off their windowsills in their houses? So that soot is entirely from boilers in the city. It's not from cars. probably 20% of it's from cars. 80% of it is from the boilers in the city burning fuel. And so we're talking about 30% of that soot is totally unnecessary. It's a pretty outrageous, there's implications to this waste that go beyond just energy efficiency and climate and comfort. So what have we done to solve this problem? You guys might be familiar with a competitor to ours, those little dials on radiators that often seem like they're not doing anything. They're called radiators, thermostatic radiator. I've been told to slow down. I have a problem speaking fast. They're called thermostatic radiator valves, and they don't really do a good job solving this problem. And so what we did is we looked at this issue from kind of an outside perspective, and it turns out that if you make a smart enclosure that can control convection around a radiator, you can control how much heat transfers from that radiator. And I'm going to spend a little time going through this. So radiators heat rooms by heating up air, and the hot air rises. And it heats rooms by radiative heat transfer. You know, if you put your hand out in front of something that's hot, you can feel heat. That's actually infrared light hitting your hand. And so 60% of it is actually the hot air that's rising. What we do is we put an enclosure over a radiator, and when we measure room temperature and we measure radiator temperature. And when the radiator is hot and the room is cold, we turn a fan on. And that fan pushes the hot air into the room, and your room heats up like you'd expect. Now, the critical thing to realize is that when the room heats up to whatever temperature you want it to be, and I'll get into how, well, you can see how you can control it with your cell phone, the fan turns off, and now the hot air can't go anywhere, it can't rise. And the air outside of the radiator, inside this radiator enclosure, heats up very hot. And so it gets to about steam temperature. And without getting too many details, and this is where you can start asking questions, if you want, or we can talk about it afterwards, the steam inside the radiator can no longer condense. And we're talking about slowing down heat transfer to that one room based on controlling a fan. We don't have to do any plumbing, there's no electrician. We can do this all by manipulating thermodynamics. Please.
Well, I'm trying to grasp why the condensation rate changes. Could you?
Sure. So I'll try not to go into too much engineering parlance, but it's a rate equation. So when you have steam in a container, if that container is really cold, the steam is going to condense really fast. If the container is really hot, it's going to condense really slow. If the container is hotter than boiling temperature, it's actually going to condense zero, right? If any water's in there, it's going to boil out. And so we're kind of shifting the equilibrium towards the lower condensation rate. And so this is really, really key. And this is really important because not only can we control the condensation rate inside of a radiator without a valve, but we also don't have to come in contact with steam. Steam is actually an extremely caustic material. Those little radiator valves, they don't last more than 2 to 4 years because the steam just eats away at any moving part until it no longer functions. So not only can we do what a TRV dreams it could do, but we can do it and have a system lifetime of 8, 10 years, whatever the lifetime of the fan is. Yes, in the back.
Do you actually need to blow air onto the radiator itself?
Intuitively, yes, but what we do is we inject cold air. The intuitive way to understand how our system works is that you have this system, and then we pull hot air out and blow it out into the room. That makes sense. And then cold air will come into the bottom. What we actually do is we inject cold air into the top, which mixes with the hot air, and then the hot air sheets out the bottom. And we do that because we don't want to expose our fans to high temperature, so that we do have those lifetimes of 8 to 10 years. So that's how we do it. And you do this in one apartment, and you can control the temperature. And you can control essentially to a flat line at whatever set point you want. And again, we grant control to every person in every room. If we install this building-wide, what happens is that when the lower floors, in some buildings, you find the hotter rooms on top or the hotter rooms on bottom. Let's imagine we're in a building that has hotter rooms on top. The hotter rooms on the bottom. Let's say those rooms heat up faster, and now you're still going to run the system to heat up the coldest rooms on the top floor, right? And in a normal building, the lower floors will just vastly overheat. What we do is we put these covers on in the whole building. We turn off the fans in the lower floors so that we stop overheating those rooms. And now steam is still running to the colder rooms on the top floor to heat them up, but we're not wasting BTUs in those lower floors anymore. And so what we end up doing is heating the building to an average temperature, statutory temperature, far more efficiently. And we've shown in our buildings that we save 25 to 35% heating costs. So these are systems that pay back in 5 years or less, depending on your fuel type. We've installed in buildings with oil that pay back in 1 year. So it really depends on what you're spending on fuel, but these are outrageously good payback periods. And some people here might be familiar with the term split incentive, where if you own a building and you want to increase your energy efficiency, typically you have to make people really unhappy to save money. In our case, what we're doing is we're eliminating that gross underlying waste that shouldn't be there at all. And so we're actually improving people's comfort while saving that energy. And a lot of people compare us to Nest. If you're familiar with the programmable thermostat, Nest claims they can save 10 to 12% in energy costs, and they do it by occupancy. Well, we can do that too, on top of the 25 to 35% we're saving, because we're not talking about occupancy. We're not talking about cooling it down. People aren't there. We're just taking away this thing that shouldn't be there at all. So this is we're a startup, so we talk a lot about our market size. This is a really big market. We waste an enormous amount of energy. There's a ton of buildings that have this technology. In New York City alone, there's 10 million steam radiators. In the United States, about 60 million radiators. Overseas, and including the United States, there's hundreds of millions of radiators out there wasting, billions and billions of dollars of fuel. And so for that reason, we show this to investors, and they get excited. This is a little bit cut off, but we work with a lot of different buildings already. We're in about 12 buildings right now. We started 3 years ago. We're really excited about the people we work with. We had the good fortune of being able to choose who we worked with because a lot of people have this problem. So we work with some names you might be familiar with. We've installed for the city. We had a really great pilot with them in a firehouse on Coney Island. We've been green lighted for deployment throughout the city, the DCAS building portfolio, so Department of Administrative Services. So we're starting now. We're small, but we're ready to grow a lot faster. I kind of talked about this already, but what solutions are out there already? What do we compete against? And you're familiar with the status quo, which is opening your window. Obviously, this is not a solution. On the other end of the spectrum, you can completely rip out all the steam in your building and replace it with hot water or forced hot air or whatever you can do. This is pretty much never done. It's extremely expensive. Even the best retrofit from a two-pipe steam to a two-pipe hot water costs an outrageous amount of money. It almost will never pay back itself, so it's only done for comfort reasons for buildings with typically very wealthy inhabitants. This is the thing I talked about before, TRVs, thermostatic radiator valves. Again, people will argue they work for two-pipe steam, and you can make them work for two-pipe type steam. We think we do a better job there. In single-pipe steam, there are no other solutions. TRVs are not a good solution. People don't do it for single-pipe steam anymore. Our system works for both, and our system doesn't care what the steam system underneath is. It works regardless. Again, I spoke about Nest a few seconds ago. Nest is not a solution for steam heat, period. Not only do we do better than them in terms of energy savings, but what are you going to connect your Nest to? Nothing. There's nothing you can connect your Nest to if you live in a multifamily building. Not a solution. We believe we are the first low-cost, effective solution for this entire market. And as an aside, as a bonus, all of our systems are digital. We can connect them to wherever we want, including Nest. So we actually create a new market for these smart programmable thermostats if people want that kind of gadget in their home. Yeah?
Do you custom fit, or is it one size fits all?
That's a great question. So if you've ever lived in more than one apartment, you know that every radiator is different size. And we have a vast array. We measure every single one. And what we do today is we custom make every cover for a specific radiator. And we do that because we want to move all of the complexity out of the apartment and into the factory. Now, it creates a logistical, I'm not going to say nightmare, but it's tough to build a rigid metal enclosure and transport mostly empty air and then get it into the right place. It's doable, and we do it today, and it's actually profitable, but we can do better. The next step for us, and we're actually engaging an industrial designer, is to create a more modular system that can be flexible to radiator sizes. We might have 10, 20 SKUs, but now we can ship not empty air, and we can assemble on site. And there's a range of solutions we can have. We'll always have every option, but in the worst case scenario, we can custom make every single one so that it's perfect. So these are some of our results. There's not enough time in most of these presentations to go into every little detail, but very quickly, we can take hot rooms, cold rooms, comfortable rooms, we can turn them into flat lines at your set point. And again, whatever set point you want, independent of whether you're in the same building. And we can do this, we can flatline this because we actually store energy inside of our enclosures. So in a normal building, your boiler turns on, your radiator gets really hot, and your room overheats, right? And then it turns off and your room cools down. And what they try to do is they try to go over and under your target set point, right? But it's always getting hotter and getting colder. The boiler turns on, already gets hot, we turn our fan on, we start pushing heat out into the room, and we slow that fan down when we get to the set point of the temperature. But when the boiler turns off, we have this huge hulking mass of metal at 100 degrees Celsius in our enclosure that we can draw heat from over time. And so we actually can flatten the overheating and underheating of apartment temperatures with our system. And that's something that no other technology can do. These are results from one of our buildings. This is one of our oldest buildings. We installed and essentially overnight reduced the heating cost by 34%. Of course, every building we install in, it really depends, how much we save depends on how overheated that building is. So we can't do magic. If your building is already operating efficiently, we're not going to magically reduce heating costs by 25 to 35%. We pre-screen our buildings to make sure that there is a problem that we can fix. And this building had a significant problem. And this saving has been, we've retained this savings for the past 2.5 years since we first installed. Yes?
I do have a question. What about private homes? So like Queens, like any out of borough?
Yeah, absolutely. So right now, just for efficiencies in our own business, we have a minimum building size of 50 radiators. We've done smaller buildings than that. It's for the efficiency of getting this out and developing our business, we're trying to minimize it. But eventually, we're building a distribution partner network where some people will be perfectly suited to servicing small single-family homes. Some will be catering to universities or very large buildings, and we hope to have it available for everybody at some point. So just to talk about the team really quickly, so I told you a little about myself. This company really started when we won the MIT Clean Energy Prize in 2012. We won $250,000 that gave us the seed fund to really develop the first system. And we've been moving as fast as we can ever since. I brought on our first non-technical employee about 8 months ago, Dave Yeskel, who has a really amazing history in energy efficiency. Has worked for the mayor's office, came from basically working with NYCERTA, contracting, just knows everybody in the industry, is a really great COO for us. And then my co-founder, Professor Kamissis, is a technical genius at Columbia University. He's the guy who kind of sat down and figured this out and helps us develop our future products. And that's really it. Just to summarize quickly, again, we're giving control and comfort to people in these buildings where they've never had it before. So we give temperature control to individual tenants where they've never been able to do that in the history of the building, which I think is a pretty big deal. Obviously, our goal here, our value proposition when we sell to buildings is energy efficiency. We want them to save money. That's how we sell this and how it makes sense right now. And there's also some subtle implications of what we're doing here in terms of asset value. And I always want to just mention this. If you can reduce, if you own a building and you want to increase the value of that asset or save money, and they kind of go hand in hand, there's not many things you can do. I don't think there's many industries that are as efficient as real estate in running their assets. If we can reduce the heating costs of a building by 30%, that's actually reducing the operating expenditure of a building by 10%. And the implications of that in asset value are immediate. And so there's a lot of things that there's a lot of value that we bring beyond just saving energy. And I spoke about a few of them, and there's more, but I always want to point that out. Yes?
What's the approximate cost they have for a 10-unit building, or do you know?
It varies. And I think I've been advised not to say how much it costs, but
Or range?
it really, I'd say 500 to 800. And it really depends per unit. And it really depends on how hard it is to install. And that's because some buildings have grandmaster keys, some don't. Some really want to cater to their tenants and have scheduling, and that really increases the cost. Sometimes you're installing in a university dorm, and you can just walk in and open every door right after the other. So it really depends on that.
How do you measure the ambient temperature in the roof?
That's a fantastic question. Right now, you ever see those guns you can point at a surface and pull a trigger and it tells you the temperature? That's an infrared thermopile. And we use that. And basically what it does is it looks at a scene and it can infer the temperature of the scene through I love talking about it. Through the black body radiation curve, it can infer what temperature you're looking at. And so we use that to measure remote temperatures in the room from the radiator. Because of course you can't measure the temperature of the radiator. You'll get an inaccurate room temperature. We're also in development of a wall sensor that's wireless and energy harvesting, so you don't need batteries. And that's kind of industry standard, and we're moving towards it. Thanks a lot, everybody.